Hello, my name is Josiah Wong, and this is my project for CS236, and we're going to be looking at KL Divergence as a detection method for adversarial attacks. So here's the poster. If you have it in front of you, you can follow along. I'm going to be including this in the corner of every one of my slides with a box around the section that I'm talking about. So let's briefly talk about what are adversarial attacks. Essentially, these are any perturbations you apply to an image that would cause a classifier to misclassify what would normally be an obvious image. And so on the left here, you can see the classifier correctly classifies this image as a 7. But suddenly, when you apply a single pixel perturbation, the classifier now thinks that this image is a 9. And so you can understand how this can cause potentially disastrous consequences downstream, especially if it's going to be impacting users. And so this is the motivation for this project, and we're going to be looking at a semi-supervised variational autoencoder and looking at its ability to detect adversarial examples and anomalies within the MNIST dataset using some derived KL divergence metrics, which we'll talk about later. And so the first question we have to ask is, why are we using generative models? The important thing here is that, at least in the case of VEs, because they're able to encode an input image into a latent space representation, we can leverage that information. In this case, it'd be via the KL divergence to extract information that would hopefully shed light on the image's integrity. We're using MNIST because it's very straightforward. The features are very clear without any ambiguous noise in the background. And so this allows us to distill our metrics on a fundamental level on a very easy task without having to worry about the complexities found in more diverse datasets such as SVHN and CFAR10. We're going to be looking at white noise attacks, very straightforward. Fast gradient method attacks, which are white box attacks that have access to the classifier. So these essentially take the back-propagated gradients and perturb pixel by pixel in an optimized way. And lastly, pixel attacks, which take a low order number of pixels and perturb only those within the image. The training conditions are very straightforward. We're just taking the vanilla model and training it on elbow and classification cross-entropy loss. And so there's nothing special here. What is special, though, is that once you do train a model, we can now derive some KL divergence metrics and hopefully use these to detect adversarial examples. And so the first metric we're going to be looking at is what I call delta. This is essentially the relative KL divergence for a given image. So we're going to take an image paired with all of its potential labels, pass it through the encoder, and then calculate the KL divergence for every combination, and then take every incorrectly labeled KL divergence and subtract from each one of those the true KL divergence value, which in this case would be y equals 3. And then from it we essentially get the relative KL divergence, and again we're calling it delta for all incorrect labels given the true label. Once you do this, we can go through the entire training or test dataset and then evaluate the statistical mean and standard deviation for delta, and we're going to call it delta bar and sigma. Afterwards, we can now evaluate a second KL divergence metric, and we're going to call it psi. And this is essentially every image's summed delta standard deviations away from their respective means. And so we're going to take an image again, find its delta values for all incorrect labels, and then evaluate how many standard deviations away it is from their respective means, and sum it across all the incorrect labels. And this will give us the psi value for that specific image. And then we can then evaluate the resulting mean and standard deviations across the entire training or test dataset, psi bar, and uppercase sigma. And so the key hypothesis here is that because we expect a correctly trained model to efficiently encode correct images, we would expect relatively high delta and psi values for a new image that is some threshold standard deviation away from their expected mean values. And in this case, we would think that this would be an abnormal or perturbed image. And so this is essentially doing anomaly detection using the KL divergence as the distribution with in order to detect statistical outliers. And we're going to find out that this is empirically the case for the MNIST dataset. And so we're going to be running tests with these empirically tuned parameters on all the proposed attacks. And after each experiment, we're going to be recording the accuracy and detection rate. And so now we can look at some of the results. On the left here, you can see what is to be expected. The accuracy of our classifier decreases with increasing strength of adversarial attack. But surprisingly, the detection rate also deteriorates with increasing attack strength. You'd expect the opposite to be true. As the attack strength increases or gets more aggressive and becomes more obvious, you would think that a detection model would be able to more easily detect these adversarial examples. But in this case, the opposite is true. For the more subtle, the more devious attacks, our detection method actually performs the best. And so this is good for this lower range, especially in the case of pixel, which is arguably one of the more difficult attacks to detect because it only perturbs such a small localized amount of the image. Across all the epsilon values, even down to 1 pixel, it can detect these successful examples with over 90% confidence rate. For the clean baseline, we have over 95% accuracy, so we know our classifier works from the get-go. And we have a 23%, 80% false positive anomaly detection rate. And so this is quite high for false positive, but the upside is that we detect a lot of the anomalous examples from our clean dataset. So if we were worried about the integrity of our classifier and worried about denoting or misclassifying images, this would allow us to improve our baseline accuracy up to 99% at the expense of discarding nearly a quarter of all inputs. And this balance point can also be tuned just by adjusting the detecting thresholds, but I just chose this in order to get a high anomaly detection rate. Now we can look at the distribution of the resulting delta values for between the clean images and successful adversarial attack examples. And so here is the distribution for our clean dataset. So this is what we would expect a non-perturbed image to fall under in terms of the distribution. And compare it to each one of these attacks which show the distributions for successful adversarial examples. And you can see how they are distinctly different both in its mean and shape from the clean distribution. And so you can understand how the proposed KL Divergence metric serves as a very quick, straightforward, and also effective method to detect a lot of these attacks, because essentially the threshold value sets essentially a boundary here on the upper end of the clean data distribution, which simultaneously would then be on the lower end of these adversarial attack distributions. And so it would be decently reliable in detecting a lot of these attacks. Secondly, you can also understand why it is important to be able to detect these attacks. If you look at these 5 images, they all look nearly the same, and yet the classifier can only correctly classify this clean image as a 0 and misclassifies all 4 of these lower images as a 3. So without a detection method, many attacks can go through unnoticed by humans, essentially. So the key takeaways from this project is that 1, we're getting a lot of good detection against noise, which is straightforward, and pixel, which is more exciting, attacks with over 90% confidence on MNIST. Secondly, while this metric is easily outshined by many other more complex detection methods, the 2 main benefits of this method is that they're both scalable and it's very lightweight with its computational requirements, requiring only an order 1 computational requirement during deployment test time. And so this makes these KL divergence metrics a potentially useful addition as an auxiliary or a peripheral defense to a pre-existing system of defenses for a given model. Future work is going to be looking at more complex data sets, such as SVHN and CFAR10, using more complex models. I ran a lot of preliminary tests using deep convolutional neural networks, but unfortunately the resulting KL divergence metrics using the proposed protocol was ineffective in detecting adversarial and anomalous examples. So more work has to be done with either tuning the method of evaluating these metrics, or perhaps increasing the powerful nature of the prior used for latent space. In any case, there's a lot of work that can be done here, but it's promising given that it serves given that these metrics perform quite well on the MNIST dataset. And that's all. Thank you for listening.